Welcome. This video will provide an overview of how to use the Runtime Controller and Progress Plotter for CindaFluent and Thermal Desktop. The Progress Plotter has been added to CindaFluent starting with version 5.8. This plotter provides real-time plotting of user-defined variables during a solution process, which is useful not only as an assessment of whether or not the solution is on track and moving towards the expected results, but also provides a tool to aid in troubleshooting a model. The plotter can help identify where a problem arises during the solution process. Such problems may be unexpected oscillations, which could result from rough user logic, or from operating at the transition region of a fluid. The plotter can also help in assessing the cause when a model fails to converge in a steady-state run. The plotter interface allows the user to change registers during the solution process. This is very useful if you have logic in the model that is triggered based on the value of a register. For example, logic which allows a graceful exit or creating additional output. The user can also modify the output settings and add additional calls for saving all data. Note that these calls to save are in addition to any existing calls to save that may be in the model. To set up the plotter, logic consisting of call statements must be added to the operations block within a model. If you are using Thermal Desktop, this is easily accomplished via a form used to select various plot options. I will come back to this chart in a moment. Let's walk through the various setup options for the plotter. First, the user must define the update interval, or the refresh rate for the plot. This is the time interval based on a wall clock in units of seconds, not based on the solution time. Please note that this input must be an integer and that a value of 0 results in plotting every time step for a transient or every iteration for a steady-state solution. Plotting every iteration or time step can slow the execution due to the time it takes to refresh a plot. In most situations, a 1-second refresh rate is sufficient. The user can also define the maximum number of data points to display for each series or line being plotted. To only view recent data, use a small value. To view a larger span of data, set this value to a larger number. The plotter includes an option to add point markers. These are squares, circles, etc. to mark each point. Please note that enabling this feature will result in markers being displayed on all data points. This is an all-or-nothing option. By default, the plot will close at the completion of a run. However, the user can opt to temporarily keep the plot open. This allows the user to review the data before closing the window. When the window is closed, the plot and all associated data will be lost. If you need to create a plot to be retained and used for reporting purposes, it is recommended you use the EasyXY plotter and create plots or plot sets. Finally, the user must specify what to plot. The plotter is set up to plot processor variables and registers. Up to 15 items can be added to a plot. Each item will use its own auto-scaling axis, even if it has the same units as other items being plotted. Note that which items are being plotted cannot be changed during the solution process. To change items, you must abort the run, change your settings, and rerun the model. When working in Thermal Desktop, you will find the plotter control has been integrated into the CaseSet Manager on the Calculations tab. Click the Plot button to access the CindaPlot Setup dialog shown here. The first step is to enable the Progress Plotter by checking the option Show Plot in Cinda Status window. Entering data into the various fields will create the necessary logic calls we covered in the last chart. In this example, the Thermal Desktop input, which is shown on the left, will result in the logic similar to what is shown on the right being added to the operations block in the CC file. I say similar because Thermal Desktop will use the processor variable names as the series labels. If you want to create a series label which is not the same as the processor variable name, you can add it as shown here on the right, where I have added labels SIL1, 2, 3, etc. Note that to do this, you must manually add the calls to the operations block instead of using the Thermal Desktop input form. Let's take a brief look at the plotter in action. I will launch a sample model, which is the transient simulation of a simple 6-cylinder internal combustion engine. As this model solves, I am plotting the temperature of each cylinder so I can observe the firing events and temperature profiles. The model was built to show a typical cycle, so the goal here is to run it for several cycles until the cycle is repeatable. As the model progresses, we can start to see each cylinder jump to the flame temperature of 2200 degrees C during the firing process and then drop back down. This profile is repeated for each cylinder based on the ignition timing. Let me pause this for a moment. Note that the x-axis, which is time, has a lowercase m after the labels. This indicates scaling of 10 to the minus third. A lowercase u indicates 10 to the minus sixth, and so forth. A useful feature of the plotter is the ability to modify inputs during execution. As an example, the flame temperature is input as a register. If I click Set Registers, I can enter the register name T-Flame. To get the current value, click on Get Current Value and then click Continue. This retrieves the current register value for inspection. Enter a new value of 2500, click the Set Register Expression button, and click OK to send this change to the processor. You can now see that the cylinder jumps to 2500 degrees when firing. Notice that each series in the plot has a unique axis on the left. As each series hits the new max temperature of 2500 degrees, the associated y-axis updates. As the processor continues, eventually all the scales are updated and we can see the cycle behavior becoming repeatable. As you may have noticed, I clicked pause again for a moment. Another feature of the plotter is the ability to modify the output options. Clicking on this button brings up a dialog which allows me to change the output interval to be every iteration or time step, or I could set a new output interval. I can also add an immediate call to save all data and then exit the run, or I can tell the processor to save all data for the next 100 iterations or time steps and then exit. This last option is useful when debugging instabilities in a model. There is also an option to return to the original settings as defined by the model file. In this demo, let's call save for the next 100 time steps and then exit. Click OK, then click Continue. Notice that nothing noticeably changes in the plot. This is due to the fact that 100 iterations flew by before 1 second on the wall clock, so my run is complete. For this demo, I selected the option to keep the plot window open for inspection when the run was complete, so I need to click Continue to dismiss the plot window and allow the processor to finish. Please note that as long as the plot window is open, the processor is still active. One last note regarding the usage of the plotter. Real-time monitoring of a run does slow the execution of a model. Although it is very useful, if you have a slow-running model, you may consider leaving it turned off, which is the default, and only turn it on when necessary. This completes today's demonstration of the Runtime Controller and Progress Plotter. I encourage you to take time to become familiar and experiment with this new tool. Please visit our website for additional instructional videos.